Hi, everybody. We're discussing today section 4.4 in Stewart, which is on graph sketching using what's called the graphing strategy, which is the handout that I handed out. A couple of things to point out. These problems are quite long. So the first one that you do, the first homework problem of this type that you tackle might take you over an hour, maybe even a couple of hours. The second one might take you 45 minutes. The third one might take you 25 minutes. The fourth one might take you like 15 minutes. So the idea is to do lots of homework problems so you get to where you can do them in a reasonable way. And the other thing is, it's normal, it's a good idea to think about, what kinds of problems to worry about for quizzes and exams and what kinds of problems to worry about for homework. The homework problems are often significantly longer than a problem that we could put in its entirety on an exam. But these really long graphing strategy problems involve lots of moving parts that can be broken off into smaller problems that could be put on a quiz or exam. And so those become very doable in the time frame of a quiz or exam. If you've done lots of practice problems where you get, this is just this one part of this big process that I've done lots of examples of. So again, you want to do as many of these hard problems as you can to get to where you can, do your homework, which is the entire hard problem, but also be ready to do smaller pieces that might show up on quizzes and exams. I won't be doing, as always, you have lots of homework. I won't be doing some things in class that are done well in the book. So for instance, one of your homework problems deals with this function, x e to the minus x. Well, there's a book example that's about x e to the plus x. So it's the same problem, basically. So I won't be discussing a function like that in section 4.4. I did discuss x to the fourth e to the minus x when we were discussing local maxes and local mins. So I have discussed some problems like that. And then look at this. I made a mistake here. This should be cos x over 2 plus sine x. So one of your homework problems is dealing with this problem, sine x over 2 plus cos x. One of the book examples is about cos x over 2 plus sine x. It's the same problem. I mean, you do need to, of course, be able to generalize something as basic as interchanging sine and cos. So I won't do all of these. And then the last thing I want to say about this stuff is that, of course, if you ever need to make a graph for anything, these days you'll use technology. You'll use a computer to make a graph. But that's not, so that doesn't mean that there's no point in studying the graphing strategy. You'll see that what this graphing strategy is really about is understanding what chunks of formulas do to graphs. So even if you're using technology to make a graph, you want to have an idea of why it came out like that. Why is there a bump here? Why is there an inflection point here? Why is there an asymptote? That's what the graphing strategy is about. Sort of training your eye so that when you look at complicated formulas for functions, they don't just seem like gibberish. You actually can look at them and understand their significance. All right. Well, I'm going to dive right in. The general idea of the graphing strategy is you start with less sophisticated analysis, so not involving derivatives. For instance, that's step one. You analyze the function. And then you go to more sophisticated things, more sophisticated as in involving derivatives. So then you analyze f prime, and then you analyze f double prime. It's not so much that the questions get harder, it's just that it relies on more sophisticated machinery, the machinery of derivatives. That's one idea, that you start with the simplest thing. And then another idea is that there's a lot on this graphing strategy. There's a lot of steps here. They don't all have to be done, and they won't all be possible, and they won't all be easy. So if you get to some step where it's it's frustrating or you're not sure you know how to do it, well, skip it. You'll have a lot of data from a lot of different steps of this graphing strategy to come to some understanding of the graph. All right, so I'm just going to dive into some examples. Function is minus x cubed minus 9x squared minus 15x plus 25. So here we go, graphing strategy. Step 1, analyze f. So the easiest thing is figure out the y-intercept by substituting x in 0 in for x. So f of 0 equals, well, if you look at that formula, f of 0 equals 25. So that means that the y-intercept is at 0, 25. So we already know a point on the graph. Now, conceptually, kind of just as straightforward as the idea of x-intercept. So we're going to set y equal to 0 and solve for x. So 0 equals f of x. That's that whole thing. Now, this is something that's not in the book's graphing strategy. I don't know why. It seems silly to not do this. It's a basic question to ask. On the other hand, it can be a pain. Like, I don't know, how do you answer this? Well, you got to factor that. So you could decide, well, the hell with it. I'm not going to do that step. I don't want to figure out how to factor that. You could. Hopefully you'll have enough stuff from other parts of the graphing strategy. I mean, I hate factoring this kind of thing. I would guess, well, I would need terms that are factors of 25. So 1, -1, 5, -5, 25, -25. I would guess x plus or minus those numbers. Turns out that it can be factored. So that's pretty cool. So the x-intercepts are at -5, 0, and 1, 0. Is there any symmetry or periodicity in this graph? Now, what are we talking about when you refer? Well, let's start with periodicity. Is this graph going to be periodic? Periodic means it repeats itself. What do you think? You say no. Why not? Yeah, what kinds of functions do repeat themselves that we're familiar with? Yeah, more generally the trig function. So it's not a trig function, so it's not periodic. Now, what about symmetry? What's that about? Anybody know what that means? There are terms called even symmetry and odd symmetry. Does that ring a bell? Well, That refers to the idea of whether the one side of the graph is a mirror image of the other side, or maybe an upside down mirror image. So that is f of minus x the same as f of x? That would be even function. That would mean that that one side of the graph is the exact mirror image of the other. Or is f of minus x equal to the negative of f of x? So one side of the graph is an upside down mirror image of the other. That's called an odd function. The answer is no. So, or neither. The answer is neither. If you plug in if you plug in negative x, you don't get the same as you get when you plug in f of x. And you also don't get negative f of x. I'm not going to get bogged down there because I think it'll be more interesting when we actually get to a function that does have that kind of symmetry. What's the domain and continuity of this function? And what about the continuity? It is where? Where is it continuous? Yeah, exactly. So the domain is all real numbers. And also it's continuous at all real numbers. Because, how'd you know that? Yeah. What about vertical asymptotes? Are there any vertical asymptotes? Emily, you're shaking your head no. Why not?
Because there's no denominator.
There's no denominator, and more generally, if you have a vertical asymptote, that's where the graph is not continuous, and there's going to be an x value that's not in the domain. So all right. What about horizontal asymptotes or end behavior? That is what happens as you go off the end of the graph, either that end where x is positive or that end where x is negative. Can somebody maybe do the hand motions for what this graph looks like? Wait a second. Try again. You got to use both arms. You can't do it with just one arm. Your whole body. I think you got to stand up. You're trying out for the cheer squad, and it's come down to this graph. You got to do the hand motions for this graph. You're all too shy. So let's. Oh, there you go. So, wait a minute. Which end is which? Okay, so here's the y-axis, here's the x-axis, here's the graph. The left end goes up, the right end goes down. Now, if we wanted to, we could write that using limit notation, but I think it's, well, our goal here is to not answer some questions about limits. Our goal is to make a graph. So there we go. The left end of the graph is going to go up, the right end is going to go down, because it's an odd degree polynomial with a negative leading coefficient. Okay, sign chart for f. Now, I'm going to do the sign chart over here. I'm going to put it way over here, and I'm going to leave it here. I move it over. And right here, I'm going to title my sign chart, and I'm going to include the formula in the title. So it's f of x, and it's minus x plus 5 squared x minus 5, x minus 1. That's the factored form. That's what's going to be useful when making the sign chart. Now, if you look on the graphing strategy, in step 1, you make a sign chart for f of x. In step 2, you make a sign chart for f prime of x. In step 3, you make a sign chart for f double prime of x. You're going to have sign charts out the wazoo, so you need to keep track of them. Especially because what you do with a sign chart depends on what it's the sign chart for. It's going to get you some information, and the information it gives you depends on what it's the sign chart for. So you're going to want to know, is this a sign chart for f, or for f prime, or for f double prime? So title your sign charts. Now, this function is continuous. Remember that continuous functions can only change sign at x values where they cross the x-axis. So at places where the y value is 0. Well, we've found those. Those x values are x equals -5 and x equals +1. So we're going to want to put the sign behavior on this graph. Now, I don't know if our book does this, but I know a lot of people don't do it. For me, sign behavior means positive or negative, or 0, or undefined. That's all important stuff to have. So you want to have all that on your sign chart, not just plus and minus signs. So I'm going to put our x coordinates, x equals -5 and x equals 1, and put down the information that we know already. We already know about those points. Those are points that cause f to be 0. And then we need to figure out the sign in between these numbers. Well, for that, we just need a sample number. So I'm going to use a sample number here, a sample number here. So there are different ways of making sign charts. I did one way last class period. Today I'm going to do this other method. So we want to pick a convenient x value. One thing that I do when I now this is important because when I if you want somebody else to make sense of your work, you're going to want to be able to show them where your signs came from. In particular, if that person is grading your work, you're going to want to be able to show them where your signs came from. So I'm not going to want to just see a sign chart with the correct signs on it. I'm going to want to see the calculations that gave you those signs. So I'm going to need x values. And one thing that I do to make my sign calculations easier is I choose sample numbers that are like exactly 1 unit away from one of these numbers. So for instance, here I'm going to use x equals -6. Here I'm going to use x equals 0. Well, for one thing, x equals 0 is just really cool. It's really simple. And then here I'm going to use x equals 2 as my sample. And then I need to compute the sign of f of x. I don't care about the exact value. I just need to know whether it's positive or negative. So my sign calculations look like this. I use the factored form. F of -6 is going to be minus a -6 plus 5 squared times -6 minus 1. So this is minus a -1 squared times -7. Notice because I chose something that's 1 unit away from that partition number, that's called, then one of my terms is actually 1 or a minus 1, which makes my calculations easy. So I end up with a minus, a plus, and a minus. So that's positive. So that means that on this whole interval, f of x is positive. Okay, let's do f of 0. Well, we already have that. F of 0 is from the y-intercept calculation. So that means that on this whole interval, the function's positive. And then f of 2, that's going to be minus 2 plus 5 squared, 2 minus 1. So that's minus 7 squared times 1. Notice again, that factor turned out to be a very convenient number. It's the number 1 because I chose a sample number that was 1 unit away. Now, we probably all know what 7 squared is, but we don't really care. All we care about is that it's a positive thing. So this is going to be a negative times a positive times a positive. That's negative. So out here, the y values are negative. Notice my signs don't alternate. On a lot of sign charts, the signs just alternate, plus, minus, but not always. You got to do the sign calculations to see. And again, I'm going to want to see the sign calculations because you got to be able to show how this stuff arises. Now, based on this stuff, we could actually make a graph. We can make a crude graph. We know 3 points on the graph. We know the y-intercept. We know 2 x-intercepts. We know that the left end goes up and the right end goes down, your left end and your right end. So at the end of step 1, you've got some information. You could certainly rule out a lot of graphs. But let's go on and do the other steps. Step 2. Can analyze f prime of x. So f prime of x is going to be minus 3x squared plus, well, that's not right. Minus 18x minus 15. Now we know that it's going to be handy to factor this, so let's factor this. Factor out a minus 3, we get x squared plus 6x plus 5. So hint with factoring, factor in stages. Factor out the constants first. I would have no idea how to guess all the possibilities of the factors of that. But this I can figure out. This is x plus 5, x plus 1. So the partition numbers are numbers that cause the thing to either be 0 or undefined. Are x equals minus 5 and x equals minus 1. So these are the partition numbers for f prime. So these cause f prime to equal 0 or f prime to not exist. They're kind of like critical numbers, but you don't have to have the test to see if f of x exists. As long as f prime equals 0 or f prime does not exist, you have a partition number. Emily, you hand up?
I was going to ask what's the difference between a partition and
Yeah, so critical numbers, we talk about critical number for the function f. That's a number that where f of x exists and where f prime equals 0 or f prime does not exist. It turns out that second thing is sometimes useful just by itself. And I forget if our book introduces this terminology. I know the business calc book uses it. So, so the partition numbers for f, maybe over here, so I should say x equals -5, x equals 1. Notice these are not, well, it turns out that -5 will turn out to be a critical number for f, but 1 won't be. But these are just the numbers that cause f to be 0 or undefined. And they're interesting because when we make a sign chart, the only place where a function can change sign is places where it either where it's either 0 or discontinuous, I should say that. These cause f prime to be 0 or f prime to not exist or discontinuous. Basically, it's just, weird x numbers. We're going to want to put those on the number line and investigate them. Sorry for not having a slicker answer about this. Okay, so we're going to make a sign chart. You're going to just continue down on your page. I'm going to go back over here, and I'm going to put the sign chart over here because I want to have all my sign charts in one place. I no longer am interested in those information about how we got that sign chart, so I'm going to erase that stuff. So I'm going to label this one sign chart for f prime of x, and that's going to be -3x plus 5x plus 1, right? That's the function. So we have two important x values, x equals -5, x equals 1, and right away put the information about what happens at those numbers. They cause f prime to be 0. And then now we need to do some calculations. So I'm going to choose sample x equals -6. I'm going to use sample x equals, and this should be -5 and -1. And so I'm going to have a sample x equals -2, and I'm going to have sample x equals 0. So again, you're just working on down your page, but I'm going to put the work over here because I don't want to get any more exercise today. So f prime at -6 is going to be that function -3 times -6 plus 5 times -6 plus 1. So that's going to be -3 -1 -5. So again, notice that term is nice because I chose an x value that was 1 unit away from one of those numbers. So I could compute this, it'd be really hard, so I'm not going to work that hard. All I care about is that it's minus times a minus times a minus, so that's negative. So that tells us that on this whole interval, f prime is negative. F prime at 0 is going to, f prime at -2 is -3 times -2 plus 5 times -2 plus 1. So that's going to be -3 times 3 times -1. So again, we don't care about the actual number, we just care that that's positive. That tells us that on this whole interval, f prime is positive. And then f prime at 0 is going to be -3 times 0 plus 5 times 0 plus 1. So that's going to be 3 times 5, minus 3 times 5 times 1, and that's negative. Notice in this sign chart, the signs do just change, minus, plus, minus. But they don't always. Remember, the previous sign chart, they don't do that. Now, what do we do with these sign charts? Well, remember I said what you do with these sign charts depends on what they're the sign chart for. This sign chart, where f is positive or negative, just tells us where the graph is above the axis or below the axis. But this sign chart that tells us where f prime is positive or negative, that tells us where f is increasing or decreasing. So we're going to use that information. Look on the graphing strategy. Horizontal tangents are at x equals minus 5, x equals minus 1. That's because f prime equals 0. So f has horizontal tangents. F is increasing on, well, let's see, what interval? From negative 5 to 1, and negative 5 to negative 1, because f prime is positive. So again, don't use pronouns. Don't say it's increasing because it's positive. Say f is increasing because f prime is positive. And then f decreasing on minus infinity to minus 5 and minus 1 to infinity, and that's because f prime is negative. And then we can get more information. Remember the first derivative test. If the first derivative changes from positive to negative at an x value, at a critical number, then that's a location of a max. So there's a local max. So I should say f. F has local max at x equals minus 1 because f prime goes positive to 0 to negative. So again, name names. Don't just say local max, or you want to hit yourself in the reader over the head with it. We're looking at a sign chart for f prime, but it's giving us information about f. F has a local max because f prime has that sign behavior. Now, inquiring minds want to know, what's the local max value? The y value is well, it's going to be y, and it's going to be f of negative 1. So that means I got to go get the original formula for the function. Minus a minus 1 cubed, minus 9 to minus 1, minus 15, minus 1 squared, minus 15 times minus 1 plus 25. I think that's it. That's the function. And it turns out if you do all that work and you don't, you're not too sleep deprived, if your cat didn't wake you up at 3 a.m., you get that this value is 32. So minus 132 is a high point on the graph. Question? All right, so that's local max. We can see that there's also going to be a local min because there's a place where f prime goes from negative to 0 to positive. That is, f goes from decreasing to horizontal to increasing. So f has local min at x equals negative 5, and that's because f prime goes from negative to 0 to positive. So we want to know what's the y coordinate? What's the local min value? That's the y coordinate. And we already found that out a while ago. That was one of the x-intercepts. That's the number 0. So -5, 0, in addition to being an x-intercept, we already knew that. We also now know that it's a low point. So that's the end of step 2. Step 3. Analyze f double prime of x. Well, f double prime of x is minus 6x minus 18. Now we know it's going to be convenient to factor that, so I'm going to factor out minus 6x plus 3. So the partition numbers for f double prime, that is the numbers that cause it to be 0 or discontinuous, what are they? On the count of 3. Ready? This is math church. 1, 2, 3. -3. What about -6? Marceline, why not? Right. When you plug in x equals -3, you get -3 plus 3. That's 0. That kills the whole thing. If I plug in x equals -6, I get -6 times -6 plus 3 is -3. So I'd have y equals 8. I'd have 18. So plugging in -6 doesn't cause the thing to be 0. So the only partition number is x equals -3, and the y value is f of -3. I'm gonna write down the calculation just so you have a reminder that when you go back to compute the y values, you don't use f double prime, because we already know that f double prime when x is -3 would just be 0. You're trying to compute the y value on the graph of f, so you go get the formula for the graph of f. So you do minus a -3 cubed minus 9 times -3 squared minus 15 times -9 plus 25. Turns out, again, if you're not sleep deprived, you get a y value of 16. If you are sleep deprived, all sorts of stuff can happen. Oh, but I kind of got ahead of myself. We're supposed to make a sign chart for f double prime. So I'm going to go, you're going to keep working down your page, but I'm going to go over here and add it to our gallery of sign charts over here in the north wing. North wing is safe. It's not ever going to get torn down. All right, so sign chart for f double prime of x, that's -6 times x plus 3. So we only need to have one partition number, x equals -3, and we've already figured out that at that spot, f double prime is 0. Looks like we're playing hangman. So let's use sample numbers, maybe x equals -4 and x equals -2. Well, I'm gonna skip ahead here. Turns out that what this is going to be is plus, and what this is going to be is minus. I'm going to skip that. I'm going to do what you're never supposed to do. You're never supposed to skip the computing signs step. But I think you get the idea how that would look. Okay, so now we're going to use that sign chart to give us information about f. So again, it depends what it's the sign chart for. It's the sign chart for F double prime, so the signs on that chart tell us about the concavity behavior of F. So I want to write conclusions in sentences. F double prime is concave up on the interval minus infinity to minus 3 because F double prime is positive. And F double prime concave down on 3 to infinity and beyond because F double prime is negative. And again, I think it's worth taking the time in the ink to, oh, this should say F. Notice what I did here. F is the thing that's concave up, and it's because F double prime is positive. F is the thing that's concave down because F double prime is negative. It's worth catching yourself and doing that. For one thing, you want it to be clear to the person reading this who might not understand as much as you do about this stuff. And you definitely don't want to say things like, it's concave up because it's positive. That's, in addition to being just not true, I must have made a mistake. How many people can spot my mistake? All right. Is that it? Is that the only one? I put Snooky in the basement. Snooky is the cat that always keeps me up at night, so I'm not as sleep deprived as I usually am. All right, so that concludes step 3. So step 4 is we put all this junk together. Now, as I said a while ago, you could actually make a crude graph after step 1, and you could improve it a bit after later steps. So I'm just going to put everything together in one fell swoop. All the points that we know. We know -5, 0, and we know 1, 0. Those are x-intercepts. We know 0, 25. That's a y-intercept. We know -1, 32. We know -3, 16. Now, what else do we know about these? Well, we know that the low point and the high point, those are places where there are horizontal tangents. So I'm going to draw those in with pumpkin spice because I don't have any red chalk. There's my pumpkin spice tangent line that's got to be horizontal. And we know that this place has to be an inflection point because the concavity changes. Now, the little graphical cue for that I like to use is to put a little X here, an inflection point. Now, get a good eraser and get used to the idea that you might want to erase your graphs and try many times. I'm a highly trained professional wearing a tie from Walmart, so I've done this lots of times. But you're going to need to think of a way of kind of organizing your thoughts. Now, let's start with the information from the sign chart for F. The graph goes from positive to 0 to positive to 0 to negative. So I'm going to do this. I'm going to say positive as in above the axis, and then it's 0 here, and then it goes back to being positive. Now I'm going to have a positive in each of those little wells. It's positive until we get to x equals 1. And then the graph goes negative, so below the axis, out here. That's the information from the sign chart for F. Sign chart for F prime, -0, +0, negative, that tells us where F is increasing or decreasing. So the information that I want to put on this graph is going to be the graph of F. So I want to put stuff about F on this sign chart. So instead of putting that plus sign or minus sign, that's about F prime, I want to do this. I want to have an arrow coming down. That's for decreasing. And I want to have an arrow going up. And my graph keeps going up until x equals -1. So this is x equals, well, and then the graph starts coming down again. And it keeps coming down from then on. Now what about concavity? Concave up until x equals -3. So in all of these wells, there should be a concave up symbol. But at x equals -3, it switches to concave down and remains concave down from then on. Like I said, be prepared for this to get ugly and for you to not like it, and maybe think of some other way of organizing your thoughts that you like better than this. I don't always do this the same way. I never really like it. I just kind of try to find the way that sucks less. So but at some point you got to get out you got to start drawing. Here again is where you're gonna want to be prepared to erase if you don't like. I need a graph that's coming down from, the left end is going up, so it needs to be coming down, concave up, and it needs to fly into that point horizontal. There we go. Now it needs to go back to being positive. It can't cross the x-axis. It's got to start going up and remain concave up until it gets to that point. Now it needs to remain positive, keep going up, but switch to being concave down and go through that point horizontal. Now it needs to start coming down, remain concave down, go through that point, keep coming down, remain concave down. In fact, it keeps coming down and remains concave down forever. That's pretty cool. Now you should expect that it's not going to be so pretty when you do it, unless you will, I could recommend go buy a cheap tie at Walmart. That helps your graphs. So there we go. That's our first example of using the graphing strategy. Now let's try example 2. F of x equals 100 over x squared plus 25. Now I'm gonna scoot along here. I'm gonna leave out even more steps. So step 1. We're analyzing the function, so f of 0, that's the easiest thing to do, is going to be 100 over 0 plus 25. So that's going to be 4. So there's a y-intercept at 0, 4. X-intercepts. So we're going to set 0. Set y equal to 0. So y equals 0, which is f of x, which is 100 over x squared plus 25. All right. Some of you probably have an answer in your head, but count to 10 before you tell me the answer. What are the x values that cause that equation to be true? Got one hand up. Should have more hands up here. 2 hands up, 3 hands up. None. Why? Yeah, the numerator is never 0. Wow. What about the domain? What are the bad x values? They're none. Can you explain why? The bottom can't equal 0. Because notice, this part on the denominator, that's always greater than or equal to 0. X squared can never be negative. So the denominator is always going to be greater than or equal to 25. It's never going to be 0. So the domain is all real numbers. All real numbers. So what about continuity? Somebody else. Where is this function continuous? Marceline?
Everywhere.
Yeah. So look, a sign chart for this function is going to be, well, there are no bad x values. There are no x values that cause this function to be 0 or to be undefined. So this function lives its whole life above the x-axis. We're not out of time, right? We got a few more minutes. All right, so what other things are we supposed to investigate here? Any vertical asymptotes? You're all packed up, so you can answer because you got nothing to do. Are there any vertical asymptotes? I've got a graph whose domain is all real numbers and is continuous everywhere. Are there any vertical asymptotes? No, good. But don't ask as a question. You got to sing it. So no vertical asymptotes. What about horizontal asymptotes? What happens when x gets really, really, really big? Can you get some more hands up? What happens to this ratio when x gets really, really, really big? Got 2 hands up. Close to 0. So what does that tell us about the graph? There's a horizontal asymptote on the right at y equals 0. What about the left end of the graph? Marceline?
Same thing.
Yeah, same thing. So the limit as x goes to minus infinity is so there's a horizontal asymptote on the left. Now don't leave yet. I know I'm facing the board, so you could leave quietly, but you can't. Because the best thing of the hour is coming up. It's where I hand out the cash prizes and I talk about symmetry. So remember a while ago I said the question of symmetry is not very interesting when the graph is not symmetric. But in this case, it's going to be an interesting result. So we're going to investigate symmetry. So we're going to investigate by calculating f of minus x. So f of minus x is going to be 100 over minus x squared plus 25. Oh, but minus x squared is just x squared. Oh, and that's just the formula for f of x. So since f of minus x equals f of x, that tells us that all the y values on the left side of the graph are going to be exactly the same as the y values on the right side of the graph. So the graph is what's called an even function. Your left side is an exact mirror image of the right side. I have 30 seconds left. I want to make a preliminary graph with what we've done so far. Remember a while ago I said you don't have to wait until step 4 to make a graph. You know, like if you've got a train to catch or a plane to catch and you got to make a graph, you could make a graph just based on step 1 results. So based on step 1 results, we know our graph has to go through 0, 4, and we know it has to have a horizontal asymptote out here and a horizontal asymptote out here. Now in between, I don't know what, but I do know it's got to stay above the axis, and I do know that the right side has got to be the mirror image of the left side. So maybe the easiest way to do this would be this. Maybe. We don't know. Or maybe, maybe we need the later steps to know the precise shape. But that rules out a lot of stuff. There's a lot of stuff we get just from, so remember a while ago I said the book doesn't have you analyze the sign of f. Just figure out where the function's positive or negative, where the x-intercepts are. It's a reasonable thing to do, and you can actually get good information. So the later steps of this will flesh this out. It turns out that it's the very simple, it's a graph that looks like a bell curve. We've actually discussed a graph that looks like a bell curve before. Thank you all. So again, these problems are hard. There's no way around that, but enjoy. And come to office hours. I have office hours today. Gabriel does as well, I think. Kingsley and Othniel have office hours. Well, check the webpage for office hours.